Okay, sorry, getting set up here. So we could talk this time about the second half of our unit testing review, or white box testing, and the concept of code coverage. So we've talked already about the idea of black box testing. We talked last time about equivalence partitioning, boundary value analysis, test-driven development, and from an object-oriented perspective. This time, we want to pick up with our white box testing or structural testing. From this perspective, we're going to talk about code coverage or path-oriented testing or different forms of code coverage today. So, in contrast to black box testing, all right, you watched the previous video. When we were doing black box testing, when the test failed, did we know what the bug was? Right? Now, if you're doing it and you have the code, perhaps you can figure out what the bug is. But remember, from a specification-based perspective in black box testing, we don't technically need the code. We need the documentation that describes what the function's supposed to do, something that describes the nature of the inputs. The inputs normally defined as the parameters to some function, some behavior, a method, the return type, any exceptions that it throws. If you're using some kind of global or stateful variable from outside the scope of the function, it's useful to know that as well. But from a purely functional unit perspective, those are the inputs, and you define what the target output is, what are the range of values based on the return value of the function, as well as under what conditions do you throw an exception. So when it fails, do you know specifically what went wrong? Well, it's a black box. You don't see inside it. You're not supposed to have. You're not supposed to necessarily have the code. So all you know is that it didn't meet those specifications, but you don't necessarily know what the bug is. We talked last time about equivalence partitions and boundary cases. Is that enough to know whether there's any faults that exist in the code? All right. By itself, if you do, we saw, constructing a full set of equivalence partitions, considering all the boundary cases, all of a sudden we got to, a good range of tests that you would have to write just to be, really confident about full scope black box unit testing. And is that enough to know whether or not there's any faults at all in the code, or do you need to know more? Well, you might notice there, I didn't say bugs, I didn't say defects, I said faults. So that begs a question, which also should be reviewed for you, but I want to talk about it up front of, what's a failure, what is a fault versus what's an error. All right, so let's make it clear, what it is we're looking for and why they're important. So why don't we start there? Failure, faults, and errors. A failure, an incorrect or unexpected output of a program, of a process. All right, so it's doing something wrong. Versus a fault, which is an invalid execution state. So the state of the program it's in a state it's not expecting to be in. And remember, the state of a program is defined as the state of its really of what it has in memory, its variables, dynamic memory allocations on the heap, what operations it's executing at the time based on what its expectations for the state of the world are, as represented by the data that and information that program manages. Now, faults may cause, failures can be caused by faults. There's no failures that aren't part of a fault, but not vice versa. But all faults don't necessarily produce failures. All right, there's some invalid execution states that your program recovers from, or perhaps just aren't critical enough to cause some kind of unexpected output. All right, failures and faults are, even look at the way they're worded, incorrect or unexpected outputs. That refers to the running program. That refers to our dynamic testing. A fault, an invalid execution state. Again, we're talking about execution. So back up here, when we talk about dynamic techniques, all right, when we talk about our dynamic techniques here for things, whether we're talking black box, right, unexpected output based on inputs helps us with our failure testing, or we're talking about today's topic in structural testing, where we're going to be concerned more with faults. Either way, these things are done while executing a program, right? Which is different than static testing, which we're going to talk about in terms of static analysis in a couple weeks. That's a process by which you test without executing the unit code. From our perspective, when we talk about failures, faults, and errors, an error is something that is in the source code artifact. So right, we take our source code files, right, and we normally send them through a compiler and produce our object code that's executed. Now, yes, we have interpreted languages, so this might be the interpreter that effectively does this on the fly, but in a sense, we get to machine level code. At the machine level code, we can exhibit at runtime faults or failures. It's source code, all right, that exhibits errors. There's something wrong in the source code, all right. That's what we normally talk of as a bug. So it has a, let me clear this stuff off. Hang on a second. When we talk about a bug or a defect in code, we're talking about an error, something that somebody did wrong, and requires a programmer to go in and make a modification to do something different. Now, errors, and even a fundamental discussion about what is an error. Okay, in one sense, you would think of as an error would be anything that could produce a fault, right? And something that's a fault could produce a failure. So a failure, something that makes the program, you get a program message, you get something wrong that you, the end user, could see in the screen, is what we think of as a failure. Not all failures, or not all faults are failures. Faults can be something, invalid program execution state, the end user may never see the ramifications of that. Those ramifications may be built over time, all right? A very well-known case study in failures was the Patriot missiles during the first Iraqi conflict with Kuwait, where the Patriot missiles were meant to knock down Scuds that were coming, and there was an accumulation error that forced them to shut down those missiles every 24 hours to reset the system, because it got over time into an invalid execution state, wouldn't calculate the proper trajectory to intercept missiles, and therefore would eventually result in a failure. All right, but not each individual fault. So there's all kinds of, we're talking about it in its simplest terms, but a fault can have several different types, and when it becomes a failure or something that you see at the system level or at the end user level, may be accumulated over time, may only happen under certain external circumstances and so forth. Well, from our perspective, if you have something that's a failure, it's an unexpected program state, it's caused by a fault, but some faults you may not see immediately turning into failures. Likewise, all errors that a developer, a programmer, introduces into source code may or may not produce a fault. Okay, or may not always produce a fault. Some of them that are particularly complex involve race conditions in concurrent code, right? If you're writing something that's multi-threaded or multi-process, there may be an error in the code that doesn't handle the logic appropriately for that concurrent scenario, but it doesn't always result in a fault. It's non-deterministic. It's a race condition, as it's called. So likewise, all errors don't wind up in an executing program based on that source code exhibiting faults. So that begs the question of, well, what actually makes an error an error? And there's different definitions of that. Some folks believe that, well, it's only an error if it could cause a fault under some conditions. It's about the runtime execution, so therefore, unless there's some circumstance under which it could produce a fault, that's the only way you would consider it an error. But if you remember Watts Humphrey, the inventor, the father of the personal software process that you did in SCR 215, he said something far more encompassing, far broader. He said a defect is anything that necessitates a change in the code. So, for example, if you have a comment that is out of date or incorrect in the documentation, right? That's not going to be seen at runtime. That's not going to cause a fault. It's I'm talking about an inline comment in the code. It's incorrect. It could mislead a developer. It could cause a maintenance issue down the road. But at runtime, it's not going to cause a fault because it's not executed. It doesn't compile into an executable instruction. One with a very narrow definition might suggest, well, that's not a bug at all. But Humphrey would say, well, if somebody has to go in and change the code in order to make it more maintainable by cleaning up their comments, then it is an error. It is a defect. Okay, so there's different interpretations even of what constitutes a software defect. And that's going to be important for us because one of the things that we're going to do throughout the semester, for example, when we do static analysis or code reviews and so forth, we are going to identify things that need to be changed in the software, in the code, in order to improve quality. Now, would you call those things errors or not? We'll talk about that. Okay, and a reminder that defects or errors can be injected at any time in the life cycle. So we're focused on quality software construction. We are in the activity of coding, but realize that those defects can be injected at any point. It could be the misinterpretation of a requirement. It could be the lack of understanding of a design. It could be a poorly written test. So there's all kinds of different scenarios in which you can inject a defect, called defect injection. In CST316, which you'll take after this course, you'll talk a little bit more about the nature of defects, the cost of defects injected in different life cycles. For the most part, in this course, we're going to refer to defects injected in the code while you're doing the construction activity. Okay, so we talked about black box testing. Let's talk a bit about white box testing. All right. In white box testing, test cases are designed, selected, and run based on the structure of the source code. In other words, this does the nitty gritty. This goes through line by line. All right. So you need access to the source code. This is about the source code instruction by instruction level testing. It is not about, it is more encompassing, more detailed than doing a black box test where we didn't need the lines of code. The actual source code in its uncompiled form. Part of the reason we need it in compiled form is we want to make sure that all the statements and conditions have been executed at least once, so we can have some confidence that each individual instruction is in some sense correct at the instruction level. So let's give an idea how you do this. All right. So first is, use the source code itself to derive the test cases. Build a control flow graph of the system, or really of the unit. System's probably too broad a term there. You should get a sense of the control flow. You can also do it from a data flow perspective. We're going to do control flow. That's more common. So you would take something like this code over here, all right, with its 8 instructions. Well, really, this curly brace, sometimes students kind of ask, do I really need the curly brace? It really doesn't matter one way or the other whether you represent a curly brace as a line of code, frankly. You don't need to do documentation. As you see in this control flow graph, I don't have a node for number 8. We left it off. We're really looking for executable instructions, right? So 1 through 7 here. Each line of code is represented as a node in the graph. Each transition, meaning the sequence in which you can execute the code, is represented by an arc. So we have 1 to 2 because in classic sequential execution, right? After we invoke this function for get second element, we're going to execute the first instruction. Node head equals get head. From this perspective, even though getHead is another function invocation, which means we could expand it, think of stepping into in a debugger. From our perspective, we'll treat getHead right now as a black box, as a single instruction. So our next instruction is number 3. If head equals null, return null. So in that case, look at number 3. It's a conditional. It has 2 outcomes, true or false. In the true case, where head is equal to null, we execute statement 4, return null. And since that's a return, which means we're going to be done with the execution of this function, we have no transitions out of node 4. Right? There's nowhere, node 4, we're done with this function, so there's nowhere to transition to in the scope of this function. So we're done. However, if the condition here is false, so head's not equal to null, then we're going to drop down to, all right, line 5, node 5. We'll do another one. If head next is equal to null, we'll also return null, which is 5 to 6 right here, right? That is this one. And again, this is a return statement, so there are no outgoing arcs. And then finally, this would drop down in the case where head.next is not equal to null, and we'd execute this return statement. So we have 3 terminating nodes, if you will, 4, 6, and 7, because there are 3 return statements. Now, never mind the fact that that's probably not very good code to write in the first place with 3 return statements. Actually, let me stay on that for a second. Part of the reason that hopefully you've been told that having multiple return statements from within the body of a method or a function, one of the reasons that it's considered bad form is because, one of the reasons bad form is you may not realize it and put some dead code after it. But another reason is it's more complex to actually write your unit tests when you have that. Those multiple terminating nodes. This is not actually a control flow graph that we want. But for the purposes of us examining what white box testing does, it's a perfectly fine function. Okay, so that's the control flow graph. Those are the different ways we can execute through the function. So now what's important for us is to talk about different kinds of code coverage in a white box test. In other words, we know we want to execute every single line of code at some point. All right, we're going to talk about that in a second. That's called node coverage. We also would like to talk about all the different ways you can get to that line of code. All right, or edge coverage, because the way in which we get to our current instruction, the path, if you will, may imply some kind of a priori condition that we need to handle. Now, in the purest form, that's actually path coverage. All right. However, path coverage we'll talk about is too computationally complex to do practically. So what is more reasonable is to consider edge coverage, meaning the immediately preceding, all right, way that we got to an instruction. So let's go forward and talk about these 3 different ways of doing code coverage. In our first case, we have a new example that we're going to use. And again, let's take a look at how this control graph is constructed. We have lines 1 through 11. Again, we didn't really worry about sorry, all right, that should work now. We don't worry about this guy. There's no 11 out here, and it really doesn't matter if you had it or not, because you'd just be dropping through anyway. Okay, so let's go through the ones that matter, right? We execute the first line, we go to the second line, we execute the second line, we go to the third line, we execute the third line, we go to the fourth line. That's why 1 through 4, linear sequence, right? Now we get to a top testing loop. The test is this. Now, some folks, might actually say there should be a 4A, a 4B, and a 4C there. I would totally agree and understand with that because these things will happen at different times. But for our purposes, we left line 4 as just line 4. The important point here is the condition, because if that condition, even on the very first iteration of the top testing loop, was true, right? If that top testing, meaning I is greater than or equal to scores.length, what will we do? We would go down to this line, right? So that's a kind of our while condition, if you will. However, if we're okay, we drop down and we start executing inside the loop. Inside the loop, we had something like what we did before. We have an if test. There's no else case. It's just a single line drop down from 5 to 6. Or if the test is not true, it skips over to 7. Here we do indicate, we do have this curly brace, and the reason why is this is something that indicates the end of the loop, and in that end of the loop we need that backward logic that a loop implies, meaning we go back to the top. All right, here, so that's right. When we hit that, we're going to go back up and do our loop test again. And again, there's no drop down, right? We never actually execute a transition from 8 to 9. We go back and do the evaluation on line 4 and then get to line 9 again if the loop test allows us to drop through. And then here we have a single return statement, so we transition from 9 to 10, and then we return from the function. All right. So that's an explanation of how this control flow graph is created. And control flow graphs don't have anything to do with what actual language you're doing to. This is basically C syntax, C, Java, whatever. Pretty much any traditional language. Now, doing something like Prolog in this, maybe not, but any kind of procedural language with step-by-step instructions you can do and create one of these control flow graphs for. Okay. First type of coverage, node coverage, or what's called statement coverage. They are equivalent. You want to select test cases such that every node in the graph is visited. So our goal, and this is a repeat of the same graph, is to identify the set of executions that we will need to do that guarantee that every statement in the source code is executed at least once. Okay, so if we're going to go through and execute this, right? In fact, I'm going to go back up. Let me erase the ink here for a second and go back to it. So, in looking at this, when I want to do a test case and execute, I can execute node 1. The first node, the second node, the third node, and I get to the test. Okay. Now I'm only interested in making sure that every single line of this 1 through 10 are executed at least once. I'm not interested in each edge yet. So I'm just doing statement coverage, which means I want to make sure that I transition from 4 to 5. I want to take this transition so I get to 5. Right? And likewise, so what does that imply first? For int I equals 0, I less than scores.length. So while I is less than scores.length, we will go on to line 5. The implication there is that I give a set of scores with an array that's not null, that's not empty, that has at least one element in it since I'm starting off at 0. All right. When we talked about our black box testing and our boundary value analysis, we had, well, let's make sure we test all the edge cases. Scores is null, scores dot, remember the basis for this one, equals 0. We talked about scores dot length being, somewhere normal or in the middle. And then we talked about scores dot length being, it's some kind of max size of the array or something like that, something large. Here we're interested in the normal case because we just want to make sure that scores dot length is greater than 1. Okay, so we can execute this loop body at least once. All right, that'll get us from 4 to 5. 5, we want to make sure that scores sub I, in this case, since it's the first one, scores sub 0, all right, should be less than the min. Okay, we had this theoretically high minimum value, but we want to make sure that that value is less than that initialized value so that we ensure that we execute 6 and not the drop-down notion of the arc. Then we want to go from 6 to 7. We'll drop down and do that automatically as we drop down the if. We get to 8 and we go back to 4 because we executed the loop body once and we're back here. Okay. Now, if I gave it a set of scores that's greater than 1, I could keep going. All right, I could go through again and again. But I've noticed how I've already executed the entire loop here. So my goal is for node coverage is to get to 9. So to get to 9, I really should have had exactly 1 value in the array. and that one value should have been less than whatever that theoretical upper bound was. So I can get to 9 as soon as possible. And we'll talk about why that's important in a minute. Once I do that, I go to 9. 9, I do my subtraction, I do my return statement, and I'm done. Okay? So that's why we get this test case. 1, 2, 3, 4, right? We went up to the loop test. We went into the loop body once, 4, 5, 6, 7, 8. We went back to 4, right? Then we dropped through to 9 and did 10, right? This is a test case. Notice the carets here. What does the carets represent? This represents a sequence. Okay? That's a sequence and stuff. Okay? That we have, but so really, this is the element. This thing is the element of a set. You remember your basic mathematical set notation. That's what curly braces are. So a test case is a set of sequences. In this case, we have a sequence of exactly one test. We were able to do one test and able to cover all 10 nodes. Okay? So we want to guarantee that we do it at least once. The second part of this is notice this minimality. All right? So we have a notion of minimality. You should remember this from your discrete math class. Minimality from the set perspective. Let me clean myself up here again. All right. When I talk about minimality from a set perspective, I'm talking about the number of elements, right? If you wrote this way of some set S, that would equal 1 in this case. Minimality is the cardinality of the set. How many elements are in it? That's where we start. That's our first notion of minimality that's important. Okay? As long as you have the number of elements. So if I had, for example, a 2-element test case, maybe somebody said, you know, I could also do node coverage if I do 1, 2, 3, 4, 9, 10, and then go back and do 1, 2, blah, 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 4 through to 8, 4, 9, 10, right? If I did that, I'm not as minimal because I have 2 elements in here, all right? Whereas this one has 1, okay? So minimality is defined as the cardinality, not how big the individual sequence is that's in here. Okay. Now there is a second part to that. We also, so even before I go to the second part, the reason why minimality is important is it means from our testing process perspective, we only have to run the code once in order to get a full node coverage to touch on every one of these nodes. Okay. Whereas if I had to do it with 2 elements or more, I have to reset up a test case and re-execute more tests, all right, in order to get there. So it's considered minimal and more efficient to only have to run that one. The second part is, so you might ask, well, isn't it important how long that sequence is? Well, yes, it is, particularly with loops. We still want to be efficient. Let me erase again. I think you guys are getting used to me trying to figure out this digitizer pen. We talked about, when I was tracing through this, the fact that we went through 1 through 4 down to 8 and went back. And yes, we could have set scores out, we could have given an array for scores that was greater than length 1 and kept going around and around as many times we want. Eventually, we would drop through. Meaning this block of statements in my test case, that would be repeated for as many elements in scores array. All right. And you might say from again, if you're thinking black box testing, you say, well, yeah, but we wanted to test it for more than one times. We had that basis dimension of array length, and therefore we wanted to test it, 2 or more times or 10 times or something in the middle to make sure of, say, something like an accumulation error. That's fine, but from a node coverage perspective, from white box statement coverage perspective, we only need to execute each statement individually once, which means a second dimension of minimality is not repeating things in here unless you have to. All right? We don't need to keep going around the scores array to get to statements 5, 6, 7, and 8 because we already touched it the first time around. Okay? Now you might say, well, there is something that's repeated here, right? Node 4 is repeated in this example. So I am repeating something. Is that minimal? It's still minimal from the sequence perspective, this individual element perspective, because I have to go back to 4 in order to get to 9. It's the only way I can get there. So therefore, it's necessary for me to visit node 4 twice in this test case. So I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 statements that I executed for a 10-line test. All right, and that's the minimal that I could possibly do. All right, so 2 dimensions of minimality. One, first and foremost, is number of tests. I said elements, but tests are elements in the test case set. Right, set cardinality. The second and less important, but still important, is the execution of the fewest set of statements to get node coverage. All right, that's my chicken scratch on there, but that's basically what it means. That's why we use the term minimal. That notion of minimal is very important. Minimal number, minimal cardinality. Minimal from a sequence is cardinality of the sequence. Okay, let's move forward. What about edge coverage, and why is it important? So you can see from a node coverage perspective that I'm not covering all the different ways I can get to something. So let's go back to our base. Well, I have it repeated here. Let's look in particular at, let's say, node 7. Right? There's 2 different ways I can get at node 7. If you remember, 5, this was the if statement. Okay. I could either have had the if be true, the condition be true, in which case I execute 6, and I drop down to 7 via this transition, or if the if condition was false, I dropped through straight to 7, right? And it may be important, right, to test whether or not, from 7's perspective, I came from 5 or I came from 6, because maybe there was something about what I did in 6 that would set up or cause the execution of 7 to be different in some way. In fact, you can generalize that to say maybe it's important whether or not the scores array is 1 element or 3 elements or 10 elements or 50 elements, because there's some kind of accumulation. We are doing a totaling function. Maybe there's some kind of accumulation that matters however many times I go around this loop, all right, that eventually would change each execution of 7. That's path coverage. We will talk about that in a second. Let's stick with the notion of edge coverage right now. And again, that notion says I want to make sure that each one of the arcs, right, each one of these guys is accounted for. Again, when I did node coverage, looking at this chicken scratch back here, I didn't necessarily have to touch each one of these guys, right? I only had to touch as many of those as I needed in order to execute each statement. So for example, in our minimal test case, we didn't do the false condition on the if tests here, right? We didn't do it because we didn't need to do it. In order to get to 7, we could get to 7 through 6 and get our statement coverage. So from this perspective, we have to change our unit test a little bit. We have to go from 1 through 4 again. We still want to, that covers a linear sequence of those. We want to make sure we cover the transition to 5. From 5 to 6, the if test. From 6 to 7, 7 to 8 to 4. If you look, this is exactly the same as what we started off with. 1 time around the loop, back to 4. However, we've got to go around the loop again a second time, right? So now we need scores.length to be at least 2, all right? Because we got to go back and pick up this transition right here, this edge. And not only that, but it's the case that for this particular test, we need to make sure that scores sub 0 is less than that starting point. And we further need that will make min equal to score sub 0. But the next time around, we want to make sure we take this transition, and again, remind you what the actual line of code was, right? This is the test. Score sub I is less than min. Min's now equal to whatever score sub 0 was. So back here, we need score sub 1. All right, score sub 1 needs to be what? We want to drop down here, so we want this test to be false. So score sub 1 needs to be greater than or equal to score sub 0. So now we have to set up the values of our array very specifically in order to force us taking this transition. Right? Now I go from 4 to 5, 5 to 7. I skip to 6. I go back to 8. I'm back to 4. Third time we're at 4. Right? But this time when I take the loop back, if I have a scores length of 2, then I'll drop down on the third test of the loop to our 9 and our 10. Right? Now, in edge coverage, by definition, since an edge in a graph, right, in your graph theory, graph is equal to a set of vertices and edges, where each edge is the connection between, actually it's a sequence, of VI to VJ. Right? What do we mean by all that mathematics? It means that we are going to touch node coverage. We are going to do node coverage by virtue of doing edge coverage. The only way that that's not true in your discrete mathematics in your graph theory is if you have a vertice that is, if you have a disconnected graph, if you have a vertice that's all by itself. Right? A disconnected graph, you'd have, a vertex connected to a vertex connected to a vertex, and then you'd have some other vertex out here somewhere, and nobody's talking to it, nobody's connected to it. We're in source code. We shouldn't have this. This would represent dead code, and we shouldn't have dead code, right? So we're assuming from our control flow graph perspective that every single node has at least one incoming edge. With that assumption, we know that edge coverage is going to be more thorough than node coverage. Further is, we're really making sure we test our logic, right? Here we were just concerned in node coverage of getting through each execution at least once. Now with edge coverage, our conditionals are really what's going to cause us to take those different paths through things. So therefore, we're really checking the logic more, the conditional logic, and that's a big source of defects in functional programming. Right? There's some variations on this. All right. So we might consider loop coverage. In other words, we may go back and say, well, specifically in a loop, we are still worried in 7, how many times we go around, whether there's an accumulated error or whatnot. We may be concerned that we are covering the test coverage case completely, all the different ways that the test coverage condition is represented. That can be important for your loops. What's actually more common and more important is this notion of condition coverage. In our tests right now, we only have one cause. We don't have a compound cause. But what if we had a test that looked like this, right? We've got this and this. If we really are worried about our logical errors, we'd actually want to go through and make sure we construct different tests to revisit these conditions and make each one of these fail, and perhaps the combination of them fail. Whether or not the combination fails then depends a little bit on the language. You can be doing short circuit evaluation. Short circuit evaluation, if this first clause is incorrect and x is greater than 100, I don't need to evaluate the second and third clause because I'm automatically going to fail this and condition, right? And on the converse, if this was an or, then the very first clause would say I don't have to continue evaluating anything else because I already know what the outcome is. Okay. From that perspective, you have to think about how many additional test cases, again, you might have to write to cover all the ways in which this condition can be evaluated. So the more you use compound conditions, the more that may complicate your unit tests as well and affect the number of test cases that you have to do. Okay, well, edge coverage better than node coverage, but like we were saying, what we really, what would be perfect is if we could do what's called path coverage, right? Select test cases such that every path, and when you think of a path, it literally means all the instruction sequences that are possible in the program, all right? And again, any instructions that cause side effects, assignment of a global variable, an accumulation value, changes to memory, all right? Anything that causes that side effect on runtime state. Another way to define side effect would be anything that causes a change outside the scope of the current set of instructions that you're testing. We would have to theoretically execute every single possible way that the program could be executed around paths, all right? Now, that doesn't mean all possible values, because we're getting back to our equivalence and boundary value analysis. But it does mean that every possible sequence of instructions. Well, think about that. Think about the combinatorics of that. Let's say that I had, a simple, I don't know, 4 instruction control flow graph, and I had a loop in here that goes from 4 to 2, let's say, right? Well, for me to do, what are all the valid set of paths? 1, 2, 3, 4, right? Back to 2, drop out. 1, 2, 4, drop out. 1, 2, 3, 4, 2, 3, 4, drop. 1, 2, 3, 4, 2, 3, 4, 2, 3, 4, 2, 3, 4, 2, 3, 4. All right, depends on how many times we're allowed to go around that loop. If you can do all possible paths, then you have much greater confidence. Let's say if there was some kind of accumulation thing that you were worried about in line of code number 3, that you'd be testing all the possible accumulations and therefore you'd be okay. But is that practical? Well, the answer is from an algorithmic perspective, your data structure is an algorithm perspective, it is not. There are far too many paths, even in a simple line of code. So for this one, even a loop that goes through 20 times, there's going to be 10 to the 14th possible paths, right? Even one test per millisecond, it would take 3,000 some odd years to test a program. And sure, you could say, okay, computers are faster now. It's one test per nanosecond. Well, it's still going to be too long, all right? It's going to take us too long to execute those paths. So instead, we have to select the most interesting paths, the most important paths. There's something that we're going to talk about in metrics as part of cyclomatic complexity, where we can talk about the concept of a basis path. So we'll get back to that. There'll be more to come on that. The other thing is this is where your black box testing and white box testing may inform each other. We may go back and say, well, the most interesting paths were actually dependent on some of my analysis of the nature of the loop itself. I want to go back to doing my null case, my 0 element case for scores, my 1 element case, my 2 element case. Maybe I go around the loop then 100 times and then I have some upper bound. All right. If I track the paths associated with each one of those by doing this, then I'm reasonably certain, hey, I should be able to reveal an accumulation error with that many. All right, type of thing. You may not necessarily know that, but at least if you're covering those different test cases from the black box perspective, perhaps heuristically applying them in your white box with the source code, you'll get a decent enough set of paths by which to evaluate something, all right? But it's not, that's a heuristic. Heuristic is an educated guess, if you will. You're going to have to do some inspection to determine if that's the case, all right? So that's node coverage, edge coverage, and what path coverage is, and why path coverage is not practically possible in a testing environment. So really we're interested in node and edge coverage from a white box unit testing perspective as developers. Even edge coverage can be difficult to identify and pull off. It's more work. So, you know, and even what tools will help you with can vary, and we'll talk about that in your lab. Okay, from returning to the object-oriented perspective is going toward kind of wrapping up on this. We talked about the object-oriented perspective in the black box testing notes, and there I gave you two approaches. The second approach actually talked about considering the state chart of the object. All right, that you remember what a UML state chart is and so forth. Considering the state chart of the object, and develops unit tests based on the valid set of states an object goes through. In fact, this screenshot, and somehow the formatting got a little messed up here, but this screenshot is actually a research tool that we did for the IG Stick project, where we identify all the states of our objects and all the transitions between them. We do this from a safety perspective, and we actually wrote a testing tool that would run through each one of the different states and each one of those different heuristic paths that we were talking about in order to understand and make sure that we touched on all the important sequences of states of the object. We still have some complexity there. I mean, when you do it from this perspective, this is not, by the way, this is not a control flow graph that you're just looking at. This is a state chart. I know it doesn't look like UML that you were doing in 315, but it effectively is a state chart where each node is a state, each transition represents an input to the program that transitions between those program states. So if I'm looking at the equivalent of node coverage there, I still have it. I have 4 nodes, and I want to make sure I at least give a path through each one of these to visit each one of those nodes. If I'm doing edge coverage, I want to make sure each of these events is given at some point. And if I want to do path coverage, I may do all possible set of sequences of these different events that I send to it. All right, so the coverage sense changes a little bit for our node, edge, path, and even negative coverage, meaning, you know, if I'm in a particular state, what happens if I try and give that system an event that it wasn't intended to see in that state? I'm in the object attempting to read state, and I get object file name does not exist input. That may not make any sense in this state, so I should at least check that I'm for that invalid transition and that the program is appropriately discarding that event. All right. So your state chart is really your guide for white box oriented unit testing. And again, you may get into some combinatorial complexity. In theory, objects can live forever. Okay, so path testing isn't computationally practical there either. So we get into, hey, can we test all the different states that an object is in? Can we test all the pairwise, all the ways I get from one state of an object to another? All right, that's quite important if you're doing object orientation, because again, in object orientation, this state transition, all right, let me clean this up here for a second. And from a pure object-oriented perspective, a pure object-oriented perspective, this state of the object is represented by the values of its class member variables. All right, so if I got class member variables X and Y, there are some particular values in some range defined for each of X and Y. And this is defined by different set of values for X and Y. And how I get from here to here is the execution of some method, or there could be some event handler that responds to some outside event in the system. So I'm executing some code. It may change the values of my class member variables, and therefore I go through my state transition. That's all stuff that you should have covered in 315. Important from an object-oriented perspective, because when I have a lot of potential ways of getting from one to another, I need to make sure from an edge cover perspective that I execute all the associated methods associated with that transition in order to validate all those edges. All right. Summary. Unit testing. So we talked about black box last time. Treats implementation of function as unknown. You're not supposed to need the code. Test for valid outputs given a range of inputs. Input, black box, you can't see inside, output. Simple as that. The science of it, how you actually figure out what test to construct there, are based on the domain range of the inputs. Domain being the basis, right? The different aspects or perspective, lengths of the array, values of the array. Remember that whole minimum discussion. And the range, the set of values allowed or even disallowed if you're negative testing across each perspective. White box that we just talked about this time, structural evaluation is the other term for it. Code coverage can be difficult. You should set a target. Do you want to do, what percent of node coverage, what percent of edge coverage, and for path coverage, again, computationally not practical to get 100% here, but how do you define important paths that you do want to cover? And do you add some more test cases associated with that? Do you actually see if your black box test can help with that if you're doing both black box and white box? All right. Tying this back into our Agile perspective. Unit testing has always been popular, existed well before Agile and so forth. Agilists love unit testing though. Remember part of our Agile philosophy in the Kool-Aid talk. If something's a good practice, we should be doing it all the time. So from Agile's perspective, unit testing is good, therefore we should unit test all the time. We should do it everywhere. So test-driven development is very Agile. A lot of Agiles like, not everybody does it, but a lot of Agiles really like it from that perspective of doing it all the time. Test a little, code a little, test a little, code a little. I mean, the finer, if you get the sense, the finer grain you do an activity in Agile, the more opportunities you have to do it rapidly and to get feedback, right? And that's why Agiles love this, because you can also automate it. And that's what your lab's going to be about. You're going to do JUnit. So you can automate. Later in the semester, we'll talk about continuous integration and testing, incorporating unit testing and other techniques into the notion of always testing your software, always having tests running somewhere to see if something's broken. We may not be able to do exhaustive testing, but if we're continuously testing on every commit, on every change, or at least nightly on every release, as opposed to only testing at the end, we're likely to find defects sooner. All right, the sooner we find defects, the less that they cost, the easier they are to fix. All right, so it's considered very Agile, and automation is considered the key. Two things I've personally seen, and I believe a lot of people agree with this. One is a lot of developers struggle to write complete unit tests. What I mean by that is they'll go out and say, well, to unit test, I need to go write, I'll write one unit test for that function. And normally I'll do it based on how I expect it's going to execute. So we talked last time in the black box about who actually writes the unit tests. And we talked about, is it the developer, him or herself, or somebody else, right? And most folks, it is the developer, him or herself. They're supposed to write the unit test before they check in, before they transition something on the Scrum board to done. So, it's just faster, it seems, for the developer to write the unit test. But again, normally then a developer's intuition will be locked into how they already designed the implementation at the lowest level. And so, they'll just write kind of the happy day or expected case for their unit test. And they won't go through the full equivalence analysis, the full boundary value analysis. They won't go through actually understanding what do I really need to set for my code coverage targets? Do I have to make sure every line of code is executed here? And am I checking that? So I see a lot that, unit testing is often seen as a kind of check the box activity where folks write the easiest and simplest and most straightforward unit test that they can. They write one, they run it, they're done, they move on. So completeness is an issue. The second is maintenance, right? We have increased our maintenance burden because as soon as we have to now do a defect fix, as soon as we do an enhancement, an incremental enhancement to something, and we have to change that code, I've got to go change the unit tests. And that's now more work, maybe much more work if I have, maybe I was really good about being complete in my unit test, but now I got to go change something. And now I've got to go rewrite, 10 unit test methods instead of one. So there's a lot of struggle to do that. Sometimes the fixes that are required, a defect fix is something that somebody needs today. It's a hot fix. So folks, it becomes a part of what's called technical debt, which we'll talk about later in the semester, meaning work you basically accumulated and think to yourself you'll get back to. So it becomes an issue, and then then folks stop running the unit tests, and then somebody else tries to pick up the code later and start with it from a new release, or you're starting a new developer on a team, and they go and they look at the unit test. Looking at the unit test, by the way, is a great way to train your new developers, except that those unit tests are way out of date, and you can't really run them anymore. Then they become crud in your system. They become a code smell, as we'll talk about refactoring. So a lot of places, a lot of developers struggle to maintain those unit tests after the first set of them done. Now, an Agilist would say, and I totally agree, that it can be a benefit. I mean, if you keep up on these unit tests, they're one of the things that actually really help you maintain better code and be able to continuously improve your code and adapt your code and react to change. All right, so yes, if you're keeping up with it, that last bullet, it actually becomes a positive, something that helps you maintain your code. But again, challenges in the face of time pressures, deadline pressures, rollover on your team, code changing hands. Once you get on the slippery slope of not maintaining the unit tests, it gets very difficult to recover. Very often you wind up scrapping a whole bunch of stuff and saying, all right, we got to go rewrite a whole bunch of unit tests all over again. So that's some of the challenges, some of the pros and cons, if you will. Black box and white box should have been review for you. You're going to do an exercise with black box and white box. We're going to use a tool for code coverage. That will be in the lab for this module, and going forward we'll start talking about some new quality coding construction techniques.